This is building query for October 23, 2020. The agenda for which Merkelizations. I think I can.
I just really wanted to make you say that. Yes, Merkelization. Yeah, today we're going to talk about a technical concept, and I think we're going to do a bit of a deep dive. It's mainly so that we can get a proper review on this and to sort of question some of the assumptions built in. So, Rico, if you don't mind, I'll just take over from here, and ideally we can get this done.
Fire away.
ASAP. Cool. So I want to start with start with the sort of statement of the problem. We want to store a larger order of magnitude of data sets on query. We want to be able to store bigger stuff. And for that reason, we need to make some optimizations to the save path of query, the way that query actually stores data. Right now, it's just not efficient enough, and it sort of has an upper bound on what it can process based on how much memory your computer has, because it eats too much memory. So aside from some changes to that to make it basically just work with a buffer instead of using sort of accumulating everything into a buffer internally, I think it's important to formalize a concept that we've been using a while and make explicit a trick that we've been using for a long time inside of query, and articulate an interface for this trick so that it can be more extensible in the future. We have a number of, I've been taking a look at our code base. We have a number of spots where if we had this in place earlier, it might have been easier to land certain optimizations in our code base that just don't exist, or that are sort of tend to be written elsewhere because of the challenging nature of this one section of our code base. The specific part I'm going to talk about today is the part of the safe path that performs Merkelization, which is the transition from a dataset document into something that is hash-based, that is an immutable data structure that is referenced by its hash. And that piece of code in our code base is very old and hasn't really been touched much because it's effectively been hard-coded for a long time. It's just been like, cool, we have a definition of what a dataset document is. We know how to turn one of those into an IPFS hash, but there's a concept built into that hard-codedness that I'd like to sort of lift up and declare today, and that's sort of what I want to get at. And so to get at the trick that we sort of need, I'm going to just quickly share my screen and start talking from there. There's one special property that query datasets really need to have that sort of puts us between a rock and a hard place. The first is we have a hard requirement that query datasets be able to be stored in a way that works like this, where they can be viewed using regular IPFS content resolution techniques. So this means that we have to use the Unix FS file system interface in IPFS. The upside that gives us is it's a great part of our universe of demoing, where we can just say, hey, go to this hash and on ipfs.io, and you're now looking at portable data. This is data that you're not using query right now, you're just using IPFS to get content, and what you're seeing is a file that's a CSV file, so you don't need any special query stuff to open version query data. This stuff is actually hash linked, but there's something special about the way that query datasets are built. And if we look at this, the hash, I'm going to copy the value of this hash. Oh no, why did I click the body? That's like the one thing that's large, and now I'm going to make their gateway resolve it. Sorry, gateway. Let's go back and forward and pray that, okay, it's cached. So if we look at the last four letters of this hash, capital Q, Z, H, M, and then we click on this dataset.json file. Hopefully this resolves. I probably should have done this locally. We'll see that the dataset.json actually makes a reference to that hash, which is the way that query datasets work under the hood. Basically, when we save a dataset to IPFS, we create this dataset.json file, which includes lists to where the components of that dataset live on IPFS. And in this case, those things are inside of this root hash, which is this giant one ending in HTA5. And so that seems like it might be violating one of the rules of hashing. The biggest rule of hashing is you can't include the hash of something inside of itself. So if I were to try to say, get the hash of hello world, and the output of that is F, I can't have F inside of hello world. And so the way that we accomplish this is actually by leveraging the fact that these files are Merkelized individually and turned into files individually. And we take advantage of that in flight as this DAG is being constructed. And so I think it helps to have a diagram of what's going on. So what we're doing when we Merkelize something is we're taking a bunch of files effectively. It's easiest to think about this as like files turning into blocks. And we are Merkelizing them. So this body.csv is a file on a file system, and we're handing it over to this process called Merkelization. And out the other side is going to come this thing, which this block effectively represents the root of the actual body.csv file. And this is a more accurate presentation of what a data set actually looks like for query, where the body tends to be rather large in contrast to the other actual data sets themselves. Each one of these blocks, if you're using linear chugging, is 2 megabytes. And so the body may have a number of blocks, and the way that it sort of wraps it all up together into one file is it makes a graph. And so we'd have all of these blocks, and each of these is sort of referenced by this one block, and this becomes the body sort of block that says, hey, if you need the body file, this is the hash that refers to that. And that is the thing that we're referencing here in body path. That is QM ZHM, as we mentioned before. And so that may be a block that refers to more blocks, but that's the root of everything you need to get the body file. And so same thing with structure. Again, structure tends to be less than 2 megs, so it tends to just be one block, and so there's no linking. And so for each of these, we're getting a hash value. So this would be, this would be, as we saw, this could be like ZHN, and then this could be, FLP, whatever. Each of these has their own hash. And then as we get up the stack, there is this dataset.json file that gets created that actually makes direct reference to the hashes of each of these blocks. And that's sort of the way that we do that right now, and the hard-coded way that we do that is we have a giant switch statement that says, hey, every time a file processes, get its hash and update this dataset document, and then and basically keeps track of the order of stuff as we're doing it. And so we have a hard-coded thing that says right now, hey, first add the body, and we actually add like the meta because it doesn't rely on anything else. And then once the body comes back, we now know we have the hash. And then we say, okay, cool, set the dataset.body path to be the hash that we just got back, and keep going. And we basically do that. We put one file in, one file out, and one file in, and one file out as we're building this DAG. And to get this root hash, we have to do the last thing, and the last step we do is create this dataset.json document, stream that in, get the hash of that, and then we tell the thing, okay, cool, you're done. You can make one giant root of this. I'm sorry if you're hearing a whole bunch of noise of construction. And so the problem that we've had with this code path is it's hard-coded. It doesn't have any sort of like terminology or language around it for how we would actually talk about this, or how we would make that a process that we could affect mid-flight. The other problem that we have is refactoring that code path is very, not only is refactoring that code path difficult, it's really inefficient right now. It's using a bunch of weird techniques and processes that are kind of really tough to optimize the way they exist right now. I would get into it, but I don't think it makes sense to reference code that is bad when we have the better solution. So what I'm going to propose is, what the PRs that I'm going to be submitting is this notion of a Merkelization hook, which is a interface that wraps files that allows you to declare dependencies on a graph as it's being Merkelized, and allows you to inject your own logic as it's being Merkelized. And so what we have right now is we have something called QFS, the file system, which is a query file system, and it declares a thing called a file, which has an interface. And what I'm proposing we add is one new function called write with hooks, which writes a file to a file system, but is sensitive to a special kind of file that has a hook declared in it. And a hook allows you to do two things. It allows you to say, hey, and this is a good example of it, I'm structure.json. And instead of just giving the hook the file directly, I'm going to wrap that file in a hook interface. And what I'm going to give it are two things. I'm going to give it, actually three things. I'm going to give it the original file, which is going to be structure.json as if nothing had changed, as if it was just going straight through. I'm going to give it a list of either sibling or children files. I can't reference parents, right? So I can't say, like if we're imagining a massive tree structure, I can't say, hey, I want to be called when I'm 5 layers up, because you can't break that first rule of hashing where you cannot modify something or have a hash contain itself. But I can say, hey, body is a sibling of structure in this graph, and so I can depend on it. If there was a folder here and there was files inside of that folder, I could depend on those as well, or I could depend on the folder itself. And what that will do is that will, when I pass that function in, it will give me a reliable timing of when that function will be called. When the function that I give it, the third thing, is passed in, I will know that at that point body.csv has been hashed. And the write with hooks function will keep track of that for me and will only call that function when that has happened. And so what that gives us is basically in process, what that would mean is like, hey, I start the process body, I start moving all of these files into Merkelization. And so I'm going to take this body thing and I'm chunking it, I'm chunking this into blocks, and all these blocks get made, and then this thing gets added, and we go, great. And then we hit the next file in the list that we're supposed to add. And in this case, we're going to add structure.json. And I see that because we're using write with hooks, we are calling, we're going to call the function. And we know that we have the hash of body. And so we're going to pass in two things to this function. The original file that you gave us, which was the structure.json file from the left. And then a list of what's been added already and their hashes. And what's really valuable about this, I think there's two really good, I think there's two reasons why this is good. The first is the interface of it. It allows us to be pretty declarative, right? Fairly declarative code that says, hey, this is what I need to do my job, and to isolate the code that modifies stuff to the component that it's affecting. And having that interface be tied to files, I think, is a much easier way of thinking. There are a number of other projects that have tried to tackle this sort of like, how do we declare information on the way into a Merkelization process? And they're really hard. Like, it's really hard to get an interface that allows you to have custom logic and is sort of like easy to get your head around, and isn't a sort of hard-coded mess. And so for us, this is really where I picked structure.json for a very real reason, because almost all of the computed fields that we need from structure.json can only be computed as the body is, after the body is finished, right? So structure.json has the length of the body in bytes. It has the, it has a bunch of other stuff that is really important. The number of errors.
Checksum.
The checksum. We can no longer calculate checksums for a reason I'll get into in a second. But the checksum used to be there. And then as another example, commit. Commit actually includes a signature, and the signature is a signing of all of the hashes as of a recent change that we've made. And that provides you with some really nice guarantees. But that means you need all the hashes to actually finish the commit.json component. And so what the interface here is I think the first gain. It allows you to declare this graph wrapped with files that are tied to business logic, and gives us this really sort of clean way of saying, all right, we can talk a little bit about how we actually do the body processing later, but I know that I need to compute structure.json in this special way, and I can only do it afterwards. The other thing that it allows you to do is it gives you hooks into very specific timing windows that allows you to do stuff as this large thing is sealing in a way that is that is faster, because we are using this technique, we can have everything happen in a single pass. And so basically we're saying, cool, have all of that stuff just go straight from the source. Like you have to remember that, like, inquiry, we're ideally having it set up so that a body.csv file could even be a URL. So it's not something that we could necessarily just like easily get again. That URL might have post requests, it might be attached to authentication. You really ideally want to have a single stream of data going in. You want to store that one time, and then once it's stored in its final resting place, you can reference it back. The upside of this is we've done a little bit of talking about how we might want to leverage the actual block layout for things later, for the construction of indices, and potentially even the inclusion of that indice within the block structure itself. By having this logic, we have access to all of that at a time that is relevant and useful, and in a manner that doesn't require us to restream stuff like crazy if we don't need to. So that's the high level version of this. It's basically just a declarative API for wrapping files with logic and dependencies. The way that this actually gets implemented under the hood is a little bit nuts, but it works well, and it allows us to sort of do something for our own code implementation that is kind of nice, because this entire write with hooks thing and the declaration of a hook file can all move into QFS. And then the declaration of all of the logic of what do we do to data sets as they're being created can stay inside of query. And that means that QFS gets a little more generically useful. There are a lot of other approaches that would benefit from being able to connect processing on data with a Merkle tree as it's being created. Creating an index is a great example. Like if you wanted to have an SQLite database that referenced all the files that you were adding to IPFS, that could be a thing that you could create. If you wanted to have a static website that took the files that you were passing to it and applied a template to all of that as input data, and then stored that template as inside of the actual, or store the executed template inside of the actual DAG itself, that would totally work too. Other stuff you can do are build block manifests. So if we wanted to actually understand what is inside of each block, or the contents of each block, it's another kind of index. But all of these things that are much easier to do and are really only possible if you are better executed in one pass if you do this with hooks. There's an alternate way to do this, which is basically just write the body, like basically do it in multiple phases, right? Write the body entirely, and then get it back, and then construct a DAG from there. What that does have a sort of two downsides. One, it's less performant because you are doing more fetching. And the second problem is it means that you have to create multiple sort of data structures inside of IPFS to get to the end result that you want. You have to sort of construct a DAG and then construct a DAG out of that DAG. And basically that means it's pushing the layout of the whole thing back up into user land. Whereas if we can do this all with the file interface, it'll stay, the construction of the DAG itself can stay down in QFS, which is a nice sort of like, in my mind, a sort of cleaving of the two areas of concern. So I'm gonna shut up now. The benefits this gets us are faster writes and easier modification of stuff. In the near-term future, I know, Asmer, you wanna write the structure, the stats component directly to the DAG itself. This would be a much easier way, right? We declare a stats file here, and we wrap it in one of these functions and say, cool, calculate stats after the body's going, or as the body's streaming. Something I haven't talked about here that should be mentioned is that for performance reasons, we actually have a second file type declared on the body. I'm calling it a pipe file, which basically just splits the file in half as it's streaming in and gives you a chance to read it as a structured entry reader on our side as it's coming through, which allows you to calculate these values as it's rolling, which is the other sort of half of the speed up that comes from our recent performance refactoring. But I can answer questions about that if you have them, but I feel like I'd rather just not talk about pipe files until we figure out this first concept. Questions? Dustin.
Okay, first, this is cool. This is definitely a chunk of code that I'm familiar with, but it's kind of been nightmarish for a long time. And this sort of change has needed to happen where it could just be abstracted out into like a piece that kind of tidies up what's really going on underneath. Where, yeah, I mean, the idea of you have a component you want to write, but some parts of that are dependent on other parts being written first and then turn into a hash. So yeah, this is a cool solution. Couple of questions. This is handling the ingress side of it, but we also have a related problem when things are coming out. That I feel like they're both, like, this is already a problem in the safe path, but I feel like the other is a slightly bigger problem only because it's like kind of all over the code base and like crops ups where like things aren't necessarily read the same way and there's like hacks kind of spread all over a query. Is there any plan for like how to incorporate
Totally. I'm going to try and go in order. First was on the read side of the interface. Yes, absolutely. I think that what I would like to see happen is...
So wait, before you answer that, for the read side, anything with IPLDs?
Nothing yet. And that's actually intentionally, the other interface I was making reference to is actually IPLD. And so the way that you declare these graphs in IPLD is you have the special syntax where you make an object with a slash key, a key whose entry that is basically empty and just a slash, and then the value is a hash that already exists. And so you, or it can be a file, I think, and it'll just do the conversion and replace it with a hash. But that's how you declare links in IPLD. To get there, I mean, for me, the fundamental point of departure here is I think that we can actually do a lot of that and keep the files metaphor. I want to hang on to the metaphor of files because I think it's easier to reason about. I think it leads to better code, and I think it lets us. Now, I think we need to overload the notion of files with these things like write hooks. And then to answer your question about reading, I think there's the notion of like a lazy reading file. Would be a really nice thing to sort of experiment with. But what I think, I was really inspired by the new Go language IOFS package proposal, which sort of basically is an attempt to declare a base set of interfaces for what a file system is, and then encourages you to write all kinds of exotic stuff on top of that and check for support of it with interface declarations. And I think that that's really the right way to go, is to effectively what we're using is a type system that is based on interfaces in the Go write time, but it could be, you could see how this would be implemented in another language using just types of files. But yeah, I think on the read side, we could totally do a lot of optimization. I would love to see a lazy reading data set that does not load anything. And we could declare files that work that way.
Yeah, I think maybe what I'm thinking about, because I might have skipped what my intention was with the question. We have problems where when we're reading in a data set, we know specific fields like transform, the README, there's another. Yeah, we know that they are like files, and we need to either, and sometimes they get inlined, sometimes they get like a local file path, and sometimes they're an IPFS path. And there has to be like an if statement everywhere. Like if those could have like a declarative way of talking about them, which probably would match exactly the ingress declaration.
Yeah, exactly.
So you could use the same declaration twice. Yeah,
and so that's where you mentioned IPLD. This notion of a declarative link and a thing that knows how to resolve itself at the point that it is called upon would get rid of a lot of that switching. And like, if this is a path, open the file. If this is a file, read it. If the file is closed, open the file again, is basically the pattern we see a lot. And so what we want to have are files that can be called multiple times and are resolving themselves as transparently. So yes, I do think that we can declare that. I think that's a separate track of work. But I do think that the general theme of using files as our interface and layering concepts that we need on top of files is kind of the right way to go for the foreseeable future. I pretty strongly believe that that's like a nicer method to work with. And I have another proposal around how I think files can actually read linked data, which is deeply inspired by the way that you explained to me how Windows piping works and how like basically Windows files can spit out structured data. I was really into that, and I want to ask more questions about that later. But to get to checksums, there's a neat thing about IPFS hashes. They're checksums. They're not linear checksums, but they work exactly the same as long as you've used the same chunking algorithm. If you change the chunking algorithm, you can have the same content but have a different hash. But if you don't change the chunking algorithm, and we won't, you can just use the hash as the checksum. They have the same purpose. The problem that we're running into, and the reason we can't calculate checksums, is they are one of the two things that are making computers choke and put a hard requirement of loading all of a dataset body into memory. Because there are no checksum algorithms there are rolling checksum algorithms, but they do not have the same basically integrity guarantees because they use a rolling window than some of the others. I'm actively interested in like researching if we can find a checksum that operates over a rolling window and gives us the same guarantees as the SHA-256. I'm sure they exist. I'm sure somebody has tackled this challenge. I haven't seen it and I can't find it. The closest I can find right now is Raven chunking, which is not the same thing. A Raven chunk does not give you a checksum. It gives you similarity hashes. And so, yeah, that's why we can't have checksums right now, because if we basically can either hard cap the size of data sets that can be created, or we don't have checksums. As far as I can tell. I might be totally wrong. There might be some algorithm out there that I don't know about. I would love to be wrong here, but
I'm confused by this, but also don't need to go into it right now. But
yeah, I mean, the long and short of it is, if you want to calculate a hash, you need to range over the entire byte stream, and so you need to have the whole string in memory at once to hash it. So while you Google,
I thought it doesn't work that way now, but
so the way that
like block hashes work like exactly as you're describing, like they do chunk by chunk by chunk, and then they like cross hash between the different blocks until you get to the end of it.
Exactly. Yeah. And so basically you almost all, like SHA-256, you need to see all of the bytes that you're going to hash at once. And so all of the bytes,
I think you can, like for MD5, I think you can literally just keep like padding on more and resumming it, pad more, resum, and do it in parts. So you can literally stream the bytes instead of like doing it in one huge pass. I'm not really sure if I'm correct here. This might be like completely broken and against all patterns. But as far as I'm aware, there are block hash algorithms that actually do that. Literally.
Okay.
We're currently using SHA-256, which I guess I've just misunderstood how that worked, because I thought that it was doing blocks
rolling. Yeah, me too. I mean, originally a while ago, and then I like looked at it, I was like, oh, this is part of our problem.
That's
yeah, and so we can just like, I have intentionally not removed the checksum field from the spec and from the structure, because we should absolutely do this so we can figure out a way to do it. And we may see a future where it's like, hey, this data set's smaller than a gig. Please calculate this checksum. Like that's also a reasonable thing to think about.
I mean, the benefit of this, at least for the save path, is when they're large, not when they're like small. Because when they're small, we can just diff them, right? Assuming the bugs don't exist. But when they're large, like because basically like, and again, this is just how Friendly works right now. It doesn't have to stay this way forever. But it'll say like, oh, your body changed by 30% or changed by 34%. But once it gets too big, it just says body changed. I don't know what happened.
Yeah. And that's, we still have the information we need to do that body changed or didn't change.
Right. So in order to do that, we would have to calculate the identical IPFS hash without storing the blocks.
No. So that's the nice thing about this hook system. You will get the hash midway and you'll know, oh, cool. And so like the refactoring actually moves the call to Friendly that you're talking about into one of these right hooks. And so you actually know the checksum. So it's true, exactly what you said. You do have to add it to IPFS, but there is a moment in the save process where you have both, and you haven't calculated the commit message yet. And
right, because the commit component, of course, yeah, needs that.
Yeah. And so you actually can calculate it right then and there and say, now we should do the friendly stuff because we finally have a checksum for both. And we have to do that anyways because we're saving. Yeah, and so that's the part where I find this like solution so far already has been a nice set of wins where stuff like that moves to what I think is a much better point in the safe process for calculation. And stuff like we want to do indexes, we want to add stats calculation, like that gets a lot easier to layer in.
Attachments.
Yes, attachments get a lot easier too. And even just like manifests of attachments, like, hey, it'd be awesome to have the commit message saying added 27 files, all right, and that's all of a sudden becomes a much easier thing to do.
Question.
Yeah, go ahead.
So the generic write with hooks that you have, it has a way to declare that there is dependencies within the structure you're writing. Does it detect cycles and just fail if it
Not yet,
sees them? Okay.
but it should. I mean, right now I'm just basically saying, so I've made sure that all the information you would need to calculate that is present, but we don't have any cycle detection. There's no, right now I'm just like, this is early days, but
I mean, that'll make it just more attractive as a third-party library. Exactly.
And I think it's a nice sort of advantage, but this gets to stuff like attachments. This will allow us to deprecate the CAFS interface and use everything on QFS file systems, which will mean that it will be a lot easier to do the repo deprecation that we're talking about, because that's one of the few things that we need was the CAFS thing. So it's a massive set of changes, but this is the most important concept that I wanted to like convey and get across and make sure that everybody wasn't like, why don't you do it this way? As Marisol, you mentioned that rsync uses a rolling checksum algorithm. Of course rsync does. Rsync's the greatest. So we should look at that. But the nice thing is we can fold that in and keep the checksums, which would be great. But the most important thing is we need to modify the safe path so it uses a constant window of memory and not accumulate the entire body into memory and then go from there.
I agree with that. That's good. Make it work good.
Yeah, make it work good. I mean, I think it's a massive change for us. It means that the size of data set you can put on query is now just limited to the size of your IPFS repo, which is really nifty. And so we can actually start to scale up into bigger data, not big, but bigger data. Yeah. Cool. That's all I had. I'm glad others are into it. That's what I'm going to be asking everybody to review. So the first PR will land in QFS that modifies QFS to have this right hook behavior. Also comes with a bunch of shifts to memfs and a bunch of cleanup that just needs to exist to get this trick to work generically. And then the second PR is this massive change to the DSFS package inside of query, which is where all of this mess is currently living. But yeah, the other thing it'll get us is by using the new file system interface, we can write to other file systems. And so now we can have queries save stuff to other places, including stuff like S3 or I don't know, weird places. But or just even an experimental local storage where we can just see what does it look like to actually have your save path also be files, which I don't know why I'd want to do that, but whatever. Yeah. So that's what I got. Questions, comments, concerns, criticisms, foibles?
One last thing. This is semi-related, but more curiosity. With the way the bodies are written, where they're turned into chunks, then you have like a node on top that links to those chunks. Do we ever get to a point where we need more than 2 layers? Like, or is that infeasible? Because like that collection of links will never be more than 2 megs.
No, it happens. It definitely happens. And particularly if you use the linear chunker, so the example that I was using actually has like 6 or 7 layers, and it makes it fairly balanced. And actually there's 2 parts to that, because you can actually, the DAG construction is configurable. You can use a balanced DAG, which balances the tree, or you can use something called a trickle DAG, where blocks are linked together where they just reference each other. Trickle DAGs are generally used for streaming video.
They're linked list, basically?
Basically, yeah, giant linked list. It might actually make sense for us to do a trickle DAG, to be honest, because
if we have indices, we don't care that it's a linear traversal.
Yeah, and so there's questions there. There will be a whole nother conversation about, we are most definitely switching to the Raven chunker. just basically because it saves us so many blocks because of the fact that we're storing structured data like CSV files. Just the Raven chunker just loves CSV files. It works really well. And so, yeah, definitely want to switch to that. But being able to tune that kind of stuff will be a really nice outcropping of this, and would be actually another vote in the column of using checksums, because as we start to tune the way that the tags are created, it breaks hashes every time. And so I want to be very careful about the way that we, because if you add something to IPFS using a different chunker or a different DAG layout, you get a different hash, even though it's the same content. And so that's,
It seems fine.
it is fine.
Because it's like a different time that it's happening. I don't know.
I don't think it's the end of the world, but
Yeah,
things like
it just-
friendly will be more sensitive to it if we rely on those hashes. Right? So trying not to
sure.
change them all the time.
Sure.
Cool. Oh, what's Asmir saying in chat? And then we can probably call it a day.
I was just going to say that, yeah, the idea of like having, because in both cases, you're like hashing data in some lossy way in order to like look for similarities, right? So it's related to diffing.
Mm-hmm.
Yep.
Yeah.
Same.
There might
concept.
be ways to like derive information from one towards the other and vice versa.
Yeah, particularly given that you have the blocks at a very important point, again, before you've for the save side of things, but for the diff side of things, I'm starting to wonder about whether we should be putting the block manifest in as like really close to the root of the DAG and just have that as an index for distributed compute.
Indices would do a lot, like SQL, compute, like fast lookups, search even, you know, like it would do a ton.
Yeah.
Yeah, there's
so
a bunch of funny stuff we can do.
Like and that's also like an insane advantage for like the way things have been lined up, like the tech, that would be hard to duplicate without having it work this way.
Yeah, if you don't have chunking at the root of your tree, your tech stack is a better way of saying that.
You're not getting all the advantages out of what you're using. Yeah.
Yeah. No, and I think that this is the upside of the sort of relationship we've decided to strike with IPFS in terms of our utilization as a library. But yeah, I think this opens up, the biggest thing that I'm hoping to facilitate here is that kind of conversation, right? What can we do now? Can we write these functions that perform these search index creation, lookup table type stuff? And can that just be like something that is done as a pull request that someone else can actually like reason about? And so that's the goal of this conversation. And yeah, I'm very much looking forward to landing this stuff. I think it will really get us up to a new scale and get us able to ship some of these better, more interesting features faster, like attachments, like indexes. Yeah. Cool.
Wild.
That's all I've got. All right. Now you know how to review this PR, or these PRs.
I feel like this is a very dense conversation, but
yeah, I
you have
apologize.
to have that sometime.
But I think it's a neat concept, and like it has extensible. It's got legs. Like I can totally see building a static site generator on top of QFS after this. That is entirely just like hooks that listen for specific types of files and do cool shit. Weekend project with all those weekends I don't have, but yeah. Anyways, neat. Thank you so much. And until next time, have a great weekend.
Query on.